Our dear learners, thanks for following up our lessons. Tell your friends to download QuestLift and you are not left behind, and you are not left behind, and you are not left behind. We are looking at double angle formulas. We've just discovered that sine of 2a, this is 2 cos, okay, can have 2 sine a, cos what? Cos a. We have also discovered that cos of 2a, this one can be cos squared a minus sine squared what? Minus sine squared a. But still, we can express this as cos, it is 2 cos squared a minus 1. It is 2 cos squared a minus 1. I call this my equation 1, and as I was ending in my lesson 9, I called this one my equation 2. Now, from cos squared a plus sine squared a is equal to what? 1. If I make cos the subject, that is cos squared a the subject, I do have 1 minus sine squared what? 1 minus sine squared a. So if I substitute for cos squared a in equation 1, my equation 1 is there, I will have cos of 2a is equal to 1 minus sine squared a. I've said in the place of cos squared a, substitute there 1 minus sine squared a. Then there is another sine squared a. Are you seeing that? So if you combine these two, if you combine those two, as you're seeing them, you do have 1 minus 2 sine squared a. This is the value of cos, that is the value of cos 2a. So that is equation 3. Now you can see that for cos 2a, it can be cos squared a minus sine squared a. It can also be this is cos 2a. This is 2 cos squared a minus 1. It can also be 1 minus 2 sine squared a. It can also be 1 minus 2 sine squared a. Now, we have sine, we have cos. How about a tan? From tan of a plus b, we saw that this is tan a plus tan b over 1 minus tan a tan b. So for a is equal to b, we do have tan of a plus a. This one is equal to tan a plus tan a over 1 minus tan a tan a. Okay, so this one is tan of 2a is equal to, when you look at this, those are the same terms. When you add them up, you get 2 tan a over, now from here we have 1 minus tan squared a as the expansion of tan 2a. So we have tan 2a, we have sine 2a, we have cos of 2a. All of them, we have them. Let's see how to apply those double angle formulas. Examples 1. Solve sine 2 theta is equal to, we are solving sine 2 theta is equal to sine theta for 0 degrees less or equal to theta less or equal to 360 degrees. Now, solution. We have sine 2 theta is equal to sine theta. 2 theta is a double angle. 2 theta is a double angle. So if it is a double angle, I can have it as 2 sine theta cos theta is equal to sine theta together. Now, from there, I said these two don't cancel out. You just rewrite them as 2 sine theta cos theta minus sine theta is equal to what? 0. We have a common factor, and that common factor is sine theta. So we have 2 cos theta minus 1 is equal to what? Is equal to 0. So either sine theta is equal to 0, meaning theta is the sine arc of 0. So what is the sine arc of 0? You look at those angles along the horizontal line. Along the horizontal line, starting with 0 degrees, we have 180 degrees and 360 degrees. Or 2 cos theta is equal to 1 from here, or it can be cos theta is equal to a half. So theta is the cos arc of a half. So cos arc of a half generates what? Shift cos arc of a half. That one will give you, we are talking of shift cos arc of a half. That one will give you 60 degrees. Remember, a half is positive. It is a positive ratio, to remind you. Or when dealing with a cos is positive in the first and fourth quadrant. So we have a 60 degrees. Then if I use the trig equation in the fourth quadrant, it will be 360 minus 60, giving you 300 degrees. So therefore, theta is 0 degrees, then 60 degrees, then 180 degrees, then 300 degrees, then 360 degrees, then 360 degrees. That is one of the applications of the double angle formulas. You can use them to solve. You can use them to solve. You can use them to solve those. You can use them to solve those. You can use them to solve those equations. You can also use them to prove identities. Prove the following identities. Prove the following. Prove the following identities. 1. Let me first list them. We can have cos squared A plus cos 2A. This one is equal to 2. We have a 2 minus 3 sine squared A. Number 2 can have 1 minus cos 2 theta over 1 plus cos 2 theta. That one is tan squared theta we have number 3. Number 3 is sine theta plus cos, no, it is sine 2 theta plus sine 2 theta, now over 1 plus cos theta plus cos 2 theta. I want to prove that that one is equal to a tan. You can see that all the ones I've chosen to look at, they have double angles in them. Let's look at the solution. Number 1, it is they want us to prove. Let me consider, if we consider the left hand side. If I consider the left hand side, I have cos squared A plus cos of 2A. Now, when you are going to prove something, try to be analytical such that you don't make mistakes. What they have given you, you have a cos squared and a cos 2. What they are telling you to prove has an element of sine. Therefore, you express these two in terms of sine. How? From cos squared A, this one is, okay, from cos squared A plus sine squared A, this one is equal to what? So if you make a cos squared A the subject, this one is 1 minus sine squared A. All together there. Okay. After that, you also deal with the cos. Cos 2A, that is a double angle. We discover that cos 2A in terms of a sine, it is 1 minus 2 sine squared what? A. So with those two, therefore, cos squared A plus cos 2A, this is cos 2A. Cos 2A is going to be, this one is 1 minus sine squared A plus this one is 1 minus 2 sine squared what? A. You can see you have 1 plus 1, that one gives you a 2. Then negative sine squared minus 2 sine squared A will give you a 3 sine squared A. You can say hence proved. Hence proved. So you can see how we are trying to prove using what we know. Let's look at number 2. Number 2, we have 1 minus cos 2 theta over 1 plus cos 2 theta. How can we prove that this one is equal to tan squared theta? Still, I'm considering the left hand side. I'm considering the left hand side. Now, they are telling us to prove a tan. Deep in your mind, you should be knowing that tan is sine over cos. So if that is the case, we can have cos 2 theta as 1 minus 2 sine squared theta, but that same thing is 2 cos squared theta minus 1. Why am I giving those two expressions? I want both to appear. The sine must appear and the cosine must appear, but since I need to prove a tan squared, the sine should be on top and the cosine should be down. Therefore, 1 minus cos 2 theta over 1 plus cos 2 theta is equal to 1 minus, in brackets we have 1 minus 2 sine squared theta, then over 2 cos squared theta. Now I have a 1, there's a 1 here, I have a 1 here, 1, then plus 2 cos squared theta minus 1. So this is 1 minus 1, I'm opening brackets, then plus 2 sine squared theta over, from here I have 1 plus 2 cos, this is plus 2 cos squared theta minus 1. That one will cancel, that one will cancel. I have 2 sine squared theta over 2 cos squared theta. That one goes away with that. When you divide, you have a tan squared theta. Then you say as required. As what? As required. All that you're doing, I'm applying the double angle formulas. You can also have one more. You can have one more, no worries. We have the third one. That third one is sine theta. I have sine theta plus sine 2 theta over 1 plus cos theta plus cos 2 theta. Cos 2 theta. I'm considering the left hand side. Now this is sine theta plus, from here we have 2 sine theta cos theta, sine theta cos theta, then over 1 plus cos theta plus, now from here I can have 2 cos squared theta minus 1 altogether there. So this one can go with that. You have sine theta plus 2 sine theta cos theta over, this one is cos theta plus 2 cos squared theta. On top, we have some common factors. One of them is sine. Actually, sine is common on top there. If you factor out sine, you remain with 1 plus 2 cos theta all over. Down here, if you factor out a cos, you have 1 plus 2 cos theta. Okay? So I'm seeing that one and that one disappearing. Sine over cos gives us a tan as required. Ladies and gentlemen, what I'm trying to say is we can use the double angle formulas to prove as many identities as you can imagine. You can also use them to solve different trig problems. You can also use them to solve different trig problems. You can use them to solve different trig problems. And one thing you should know, you can see in my proofs, I'm using all the identities. If you look at this, no, it is here. If you look at this, this is, no, not that one. I've used cos squared theta plus sine squared theta is equal to 1 several times. Reason, we build, it is a build up. We start from somewhere. One identity can lead us to another. That is it. We keep using them to, I've said we keep using them to prove, to show as many identities as you cannot imagine. Let's link up in our next lesson.